A very good day to all of you. Okay, today we are going to learn the surface integral of scalar field. Okay, let the capital S here be a surface with equation z equal to gxy, and let R be its projection on xy plane. If gx and gy are continuous on R and f is continuous on S, then the surface integral of f over S is given by the double integral f x y z d capital S, okay, over the surface S. And to evaluate the surface integral here, we replace back z is actually function of gxy. Okay, ds is one unit of the surface area. Okay, remember, okay, defines the surface area of the surface z equal to gxy in double integral as the square root of 1 plus gx squared plus gy squared dA over the region R. Means when you press a surface on xy plane, you get the region R here. Okay, notice that if your fxyz equal to 1, okay, you get actually is a, this is, okay, 1 d capital S over the surface S. This is actually equivalent to what you have learned in double integral to find the surface area of the surface Z equal to gxy in double integral as a, where the ds is actually square root of 1 plus gx squared plus gy squared dA over the region R. This represents, okay, the surface area of the surface Z equal to gxy. Okay, but this is in double integral. Okay, but now, okay, we have the surface integral fxyz ds. Okay, d capital S here is one unit of the surface area of the surface z equal to gxy. Okay, and then, okay, what's the meaning of this surface integral? Okay, what we call this is a scalar form. It's actually, okay, the surface integral here is actually, you can view it as a mass of a lamina in 3D space. Okay, let the mass of a homogeneous lamina, okay, the M is actually, okay, the rho multiply the A, because lamina is a thin sheet, consists of area only without volume. Okay, if you have an inhomogeneous lamina in 3D space, let the density function is rho xyz. Got inhomogeneous, it's not constant density. The density is depend on the, okay, the function of x, y, z. So a unit mass in 3D space will be delta mi is a rho, okay, xi, yi, zi multiplied delta si. Okay, because lamina, you have the density and area only. Okay, and now your lamina is not in 2D, okay, not in 2D, yeah? 2 dimensions, but in 3 dimensions. Okay, so in 3 dimensions, okay, a lamina in 3 dimensions which consists of, okay, area, but we calculate the area in 3D as a surface area. Okay. And then, okay, if we sum out, okay, the 1 unit of the mass, okay, of the lamina, okay, from 1 to n, and the n approaches infinity, this is actually equivalent to the surface area integral of rho xyz d capital S. This is k d capital S. If the line integral of scalar field, we have the d lowercase s, stand for 1 unit of the arc length. Okay, d capital S, okay, capital S here stand for 1 small unit of surface area. Okay, when we sum out, okay, we have, okay, I from 1 up to n, and we have infinite many where the n approaches infinity. This approximates to the surface, okay, integral of scalar field over the surface S. So means, okay, surface area, okay, of scalar field here represent the mass of lamina in 3D space. Okay, example 1, okay, a cone-shaped surface lamina S is given by Z equal to 4 minus 2 third x squared plus y squared. Okay, and the cone strip case space lamina here is bounded from z equal to 0 until z equal to 4. At each point on S, the density is proportional to the distance between point and the z-axis. Find the mass of the lamina. Okay, so the mass of the lamina is given by the surface area, okay, the density function xyz d capital S over the surface S. Okay, where the surface S is actually given by the cone strip z equal to 4 minus 2 sec x squared plus y squared. Okay, so this is a shape of the lamina. Okay, this is projection of the lamina. Okay, projections happen because lamina bounded from z0 until z4. So when z0, okay, plug in z0 into the lamina equations. Here, you plug in z0, so you have 0 equal to 4 minus 2 times sec x squared plus y squared. Okay, and then so you bring the negative 2 sec x squared plus y squared to the other side. Okay, so you have 2 times sec x squared plus y squared equal to 4, and then you square both hand side. You have 4 times x squared plus y squared equal to 16. Hence x squared plus y squared equal to 4. Show that this is a circle centered at origin with radius 2 units. So when z equal to 0, you get actually is a circle centered at origin with the radius here 2 units. Okay, means the r is actually from 0 until 2. And then you have a full circle. That's why later on the theta will be from 0 until 2 pi. Okay, when you substitute z equal to 4, because the lamina bounded from z0 until z equal to 4, when you substitute z equal to 4 into the lamina equations, so you have 4 equal to 4 minus 2 times sec x squared plus y squared. Okay, cancel the 4 here. That's why you have 2 times sec x squared plus y squared equal to 0. When you square both hand side, they give you 4 times x squared plus y squared equal to 0, implies that x equal to 0, y equal to 0, and z equal to 4. That's why you see that this is a lamina of shape, the cone shapes with the maximum point is x0, y0, z is equal to 4. Okay, remember what you want to find is the mass of the lamina. Okay, mass of the lamina is given by the surface integral rho xyz d capital S over the surface S. Okay, now how to find the density functions rho here? Okay, that's it. Okay, and you said at each point on S, the density is proportional to the distance between point and the z-axis. Okay, density is proportional. Okay, so we let it equal to k time of the distance between point. Point means the any xyz point and the z-axis. Okay. Okay, let's say have this. Okay, we have this is a x-axis, is the y-axis, vertical is the z-axis. Okay, on xy plane. Okay, this is a point xy0. Okay, when you raise up to about z unit of height, you have the xyz. So your lamina is proportional to you have xyz. Lamina is actually proportional to a distance between the point xyz and the z-axis. So any point xyz, lamina is proportional to a point with a distance z, with a distance to the z-axis with a distance. So this is a distance r that we are going to find, and we notice that this r when you project it down, this is a r on the xy plane. Okay, this is r like the polar coordinate, or you can solve the distance of the r here by Pythagoras theorem, which is the square root of x squared plus y squared. So r is the sec x squared plus y squared. Hence density function is actually k times of square root x squared plus y squared. Because as in the statement said, density is proportional. That's why the rho x, y, z is k times of the distance between point and z-axis. Distance between any point with the z-axis is given by the r. R is actually from the radius of a circle, which is actually square root of the x squared plus y squared, where you obtain it from the polar coordinates. Okay, so you already have the rho x, y, z is actually k times of surd x squared plus y squared, k ds. Okay, 1 unit of surface area is given by 1 plus gx squared plus gy squared dA over region R. The region R is a circular area with a circle with radius 2 units, and it's full circle. Okay, that's why later on, your dA become, you use a polar coordinate r dr d theta, and the region R is a circle. Where you solve it when z equal to 0 in previously, z 0, you get is a circle with radius 2 units. That's why the region R later on, we are going to solve it using polar coordinate, where the limit of r from 0 to 2, limit of theta from 0 to 2 pi. Now we are going to solve, find what is a gx, what is a gy. Gx is actually from the surface, the surface z. Gxy is actually equal to the z equal to 4 minus 2 times surd x squared plus y squared. You want the gx squared, so mean you need to find delta x g or delta x your z. Mean you find del z del x. So delta x 4 is 0. You delta x negative 2 times surd x squared plus y squared. When the delta xy is constant, so you delta x4 you get 0. So delta x this term, remember this is power, you have negative 2. Square root is power half. So for differentiation power, you bring become multiply. So you have half, and then x squared plus y squared power half minus 1. Differentiation, so half minus 1 become minus half. For differentiation, initially this is power half. So half minus 1 become minus half. And then you have to delta x inside the square root. When you delta x squared, you got 2x. You delta xy squared, you have 0. So you simplify it. Here we have negative 2x. Power negative half become over square root x squared plus y squared. Gy is similar, it's only inside here, you delta y x squared plus y squared, get 2y, that's why you get negative 2y over surd x squared plus y squared. Once you plug in, you need gx squared. Gx squared, so it becomes 4x squared over x squared plus y squared. So gx squared becomes 4x squared over x squared plus y squared. Gy squared becomes 4y squared over x squared plus y squared. And then for 1 here, you multiply by x squared plus y squared. You divide by x squared plus y squared. Hence, you have the same denominator. We combine it as one fractions. This one for 1. And then x squared plus 4x squared, total have 5x squared, y squared plus 4y squared, total have 5y squared. And then factor out the x squared plus y squared, you cancel. Here you have surd phi dA. So where k is constant, surd phi is constant. You may factor out surd phi k. Since the region R is circular, so you use polar coordinate r d theta. And as mentioned just now, the region R, how you get region R is actually the projection of the cone z equal to 4 minus 2 minus surd x squared plus y squared. Here will be on the xy plane, happen when z equal to 0. Solving it, let z equal to 0. When you solve it, you get the x squared plus y squared equal to 4. Hence, the r is actually from 0 to 2, and it's full circle theta from 0 to 2 pi. 0 to 2 pi. So we integrate this total r squared, we get r cubed over 3. Okay, plug in the limit of r. So we have here 8. So 5 times 8, k divided by 3. Okay, lastly integrate 1 d theta. From 0 to 2 pi you have 2 pi. So total is 16 pi k pi over 3. Okay, the second example, evaluate the surface integral y squared plus 2yz d capital S over surface S, where S is the first octant portions of the plane 2x plus y plus 2z equal to 6. Okay, this is a plane tetrahedron plane. Okay, in the first octant, so mean x positive, y positive, z positive. Okay, to know, okay, let's say the x-intercept, you let y and z 0, 2x equal to 6, hence x is equal to 3. This is x-axis. Okay, and then to know, okay, your y-axis, you let x and z 0, that's why y is 6. Okay, and then to know, okay, the z-intercept, you let x and y 0, that's why 2z is 3, so z will be 3. 2z, sorry, equal to 6, so z will be equal to 3. Okay, to get the projections R, okay, let z equal to 0. Okay, that's why y equal to 6 minus 2x. Okay, this is the region R here. So x, okay, 0 to 3, 0 to 3 means, okay, x, when x 0, so y equal to 6. So when y 0, x equal to 3. Now 6 minus 2x equal to 0, so x equal to 3. So this is the region R. Okay. Then to evaluate this surface integral, you need to plug in z, okay, from the plane, okay, equation. You need to solve z here from 2x plus y plus 2z equal to 6. Okay, gxy is equal to the z equal to 6. Okay, minus 2x and minus y divided by 2, or 3 minus x minus y over 2. Okay, gx is actually you del x. Okay, del x the z here, so you have negative 1. Gy is actually you del y the function z, you have negative half. Okay, and then the surface integral y squared plus 2yz. Surface integral actually lastly you have to eliminate the z variable because you are going to solve it become double integral. So z, okay, you have to replace z from here. 6 minus 2x minus y. 6 minus 2x minus y over 2. And then ds, okay, d capital S is square root 1 plus gx squared plus gy squared dA. So gx, okay, squared. From here, gx is negative 1, so gx squared we have 1. Okay, gy squared. Gy is negative half, gy squared will be plus 1 over 4. Okay, and then so 2 and 2 here you cancel, so you have y multiply 6 minus 2x minus y. Okay, you solve the square root 1 plus 1 plus 1/4, so total is at square root 9 over 4 to become 3 over 2, 3 over 2, and then you expand, okay, this in the bracket. So y squared plus 6y minus 2xy minus y squared. So y squared cancel. Okay, you just left actually 6y minus 2xy. I factor out 2y. So 2y times 3. So total 6y minus. So I got, yeah, correct. 6y. So factor out 2y, you still have 3 here for this term. For 6y, I factor out 2y, so 2y times 3, 6y. So 2y times negative x, we have negative 2xy here. Okay, and then so the 2 and over 2 here cancel, left 3. Time of integral 0 to 3, integral 0 to 6 become 2 times, factor out 2 times 3 minus x. Then integrate y times 3 minus x dy dx. Okay, when integrate respect to y, 3 minus x is constant. So you integrate, okay, constant times y, you have a constant, okay, times y squared over 2. Okay, substitute, okay, y from 0 to 2 times of 3 minus x. Okay, so you plug in, okay, this one, 2 squared, you have 4, and then 3 minus x squared times 3 minus x dx. So 2 and this 4 cancel, 2, 3 times 2, you have 6. This is 3 minus x squared times 3 minus x power 1, total is 3 minus x power 3. Okay, to evaluate this one, you may use a scientific calculator or you may use a substitution technique. U equal to 3 minus x, then du will be equal to negative dx, hence integral of 3 minus x cubed dx. Okay, dx replaced by negative du. So 3 minus x u, so this is u cubed. So integrate, okay, negative u cubed, you got negative u power 4 divided by 4. Put back the u is 3 minus x, okay, so power 4 divided by 4, that's why here the result is 3 minus x power 4 divided by negative 4. Okay, plug in the, okay, upper limit, so 3 minus 3, we got 0. Plug in lower limits, okay, so it's minus 3 power 4, 81. Okay, and you simplify it, you get the answer is 243 divided by 2. Here become 2, this become 3. Negative and negative positive, 3 times 81, so 243 divided by 2. So this is the surface integral of scalar field. In this form, okay, we conclude back what we have learned. Surface integral of fxyz ds is actually represent the mass of lamina in 3D space. Okay, 3D space where the fxyz represent density function, then this surface integral represent the mass of lamina in 3D space, because d capital S here is 1 unit of surface area, 1 unit of surface area as you obtain in double integral. Okay, the surface area ds is actually formula square root 1 plus gx squared plus gy squared dA if the surface is given by z equal to gxy. Okay, this actually represents the mass of lamina in 3D space with an inhomogeneous density function. So you have density times the area become the mass of lamina in 3D space. If the fxyz equal to 1, this is actually the, okay, surface area S. Surface area S, okay, of a surface given by z equal to gxy. Okay. Then, so we have gone through the 2 examples. So means to solve your surface, okay, area as surface integral of scalar field. So first of all, you must identify your z, okay, okay. So z equal to gxy, and then define gx, define gy, plug in to get your ds here. Okay, and then if you got variable z, you must replace in terms of function of x and y. And then, okay, you must identify the region R, because later on it become double integral dA over region R. To get the region R, you need to project your surface on your xy plane. Okay, hence Depend on your region R. If circular, then you use polar coordinate. Okay, if not, you use Cartesian coordinate. Okay, with this, thank you for your attention and watching this video.